Thanks, Rainey. So thank you for the invitation. This is a really lovely venue, so I'm happy that we chose to come here. So what I'm going to do today is tell you about some of the work that we're doing in granular materials, but I'm also going to save about 10 minutes at the end to have Chad Giusti come up and tell you about some of the future directions that we have. So I'm going to start off with giving you a flavor for the kinds of problems that we're working on. This is in collaboration with Karen Daniels at NC State, Eli Owens, Lisa Manning at Syracuse, Mason Porter at Oxford, and then Chad and Rob at Penn. So the problems that we work on are in collections of particles. So we traditionally work on particles that are collapsed into a two-dimensional space. So they're contained inside of a little box, and they're usually two different sizes, two different diameters of particles. They're photoelastic, so we can use birefringence measurements to estimate the amount of force between these different particles. So although they look sort of randomly dispersed within this two-dimensional space, if you look at their forces between them, you can see this beautiful branching pattern. So this branching pattern is called force chain structure. And what's really interesting about this type of material is that particulate models and continuum models seem to have some difficulty in predicting some of the bulk properties of these materials, including acoustic transition. And we think that that's potentially because of this heterogeneous structure inside of the material. So one of the questions that we have in the field is how can we characterize this heterogeneity and this force chain network structure in order to better understand the bulk properties of the material. So the way that we go about doing that is that we take this type of data and we put it into a network framework. So we treat each of the particles as a node in the network, and then the edges between the nodes are equal to the forces between the two particles. So what we have is a couple different measures. A is the contact network, so that's whether or not two particles are in contact. W is the force network, so each element in here tells you the force between node I and node J, or particle I and particle J. And then I'll use omega to indicate the mean force. So what we're going to do is we're going to ask how can we quantify the structure of this network in various ways and see if we can understand bulk properties a little bit better. So, yeah. Oh, these are piezoelectrodes, so they're basically to estimate the amount of force at a very precise scale. And then we use them to calibrate the forces throughout the entire picture.
So those gray balls in the middle picture are the same places?
Yes, they are. Yep, exactly. Yeah, and you can see them even better here. These little red balls are the same thing. So it's for calibration. Okay, so what we did initially is that we just took a lot of different statistics that have previously been defined in network science and asked what kinds of dimensionalities they're able to access inside of the material. So we used, for example, a global efficiency measurement. This is actually the 1 over the path length between the shortest path between nodes I and nodes J. And what you can see here is that you actually get a really nice radial picture. So particles that are in the center have a shorter path length to the rest of the system than particles along the edge. That's a very obvious measurement, right? So it's very intuitive, is that you get a radial system-wide picture. Then what we did is we also used, I guess I don't really need this because I can just stand and point. We also used this modularity equation to estimate the community structure inside of a network. So community structure identifies patterns of particles that are densely interconnected with each other, and then finds the boundaries between these communities where there's weaker connectivity. What it does is that you maximize this modularity quality function, which is a difference between the adjacency matrix and a null model. So if you maximize the difference between these subject to having node I in partition GI and node J in partition GJ, then you can identify these two-dimensional domains inside of the material. So that gives us a two-dimensional picture. What it's saying is that inside any of these colored sets, we have dense connectivity or dense force, and then along the boundaries between these sets, we have weaker forces between particles. So it enables you to quantify that separation between different pieces. We can also use geodesic node betweenness. So this estimates the number of shortest paths that go through a particular node. So if I want to get from, let's say, node I here to node J, how many of the paths that go from this side to this side have to pass through node V? And that if that number is very high, then node V has a high betweenness. And we can plot that out in the two-dimensional space, and we can see these one-dimensional curves. So these are particles that where a lot of shortest paths throughout the network have to pass through. And we can see that captures a different dimensional structure than the modularity or than this system-wide measurement. Finally, we can use a clustering coefficient. So that quantifies the number of connected triangles divided by the number of connected triples. So it's really a measure of very local connectivity structure. And in that case, we can see that we can pull up specific particles that have dense connections right around them in their very local neighborhood, but it's agnostic to connectivity far away from the particle. So it enables you to quantify connectivity at the very local level of single particles. Yeah?
In the modularity,
yep.
How do you go from this queue to the, it looks like you have clusters there. Am I
That's right. So you maximize this queue subject to the constraint, well, so maximize the difference here, having node I in the community GI and node J in community GJ. So it's basically finding a partition of particles into communities that maximizes this function.
And is it this mirror? This looks like graphical Laplacian, this adjacency matrix minus something. Is this a spectral clustering assumption?
It's related, but it's not exactly a spectral clustering. Yeah, you could do spectral clustering as well, and it's similar, but not exactly the same. Yeah.
And for all these measures, is it just the adjacency matrix, or is it weighted by the force values?
You can do it in either case. For this particular set, we used the weighted connections. So actually, I should have W in here instead of A. But you can do either. So we thought that this was sort of interesting because we can use these traditional network statistics to quantify a couple different dimensions or scales of structure inside of the network. And then the question is, could we use this to understand bulk properties of the material? So we have some experiments from Karen Daniels where she has these particles in the two-dimensional space, and then she uses a driver to input an acoustic signal at the bottom of the packing. I'm just going to play it for you one more time so that you can see that structure again. Okay. So what's interesting about this, I'm going to play it again, is that you can see that the acoustic signal seems to travel along the force chains, the strong force chains, but it also travels radially along the weak particles as well. It seems to do a combination of both of those things. So just watch one more time. Okay? And
calculation, not a measurement.
It's a measurement. It's a measurement, yeah.
How do you get that much detail?
Yeah, so the way that you can do it, well, the way the experimentalists can do it is that, so you put the acoustic signal in here, and then you do the birefringence measurement. So you can basically, because these are photoelastic, when the acoustic signal passes through, they'll squish a little bit, a change in the intensity of the light. So you're just actually looking at changes in intensity of light. And then on the right-hand side is
a special circles. You've added some circles.
Those circles are, again, they're piezoelectrodes, so they're basically quantifying, they're for calibration of the amount of force that we have. And then here is a packing that has higher pressure, so I'm just going to show you the acoustic signal transmission there as well, just so that you can see it's a little bit different. Okay. So it travels less so along force chains and seems to be a little bit more radial in its structure. So the question is, can we understand some of this acoustic transmission using the network statistics that I showed you before? So it turns out yes. So this is the actual signal, the acoustic signal that's put through. It's actually 5 sinusoidal waves, and then we allow the acoustic signal to scatter. So we have 2 domains here, the injection of the sound and then the scattering of the sound. And then we quantify the amount, the correlation between the efficiency of the particle in the system and signal intensity. And what we can see is that during the injection phase, there's a very strong correlation. So this means that particles that have a high efficiency tend to also have a high acoustic intensity, whereas in the scattering phase, regions that have high efficiency don't seem to have a high signal intensity. So this particular statistic is able to separate out the difference between the injection phase and the scattering phase of the acoustic signal. And we actually saw the opposite finding in using the two-dimensional domains. So in this case, what we have is that during the injection phase, the community structure is not a good predictor of acoustic transmission, whereas in the scattering phase it is. So let me give you an intuition for why that's the case. So what we think is happening is that in the injection phase, the acoustic signal is traveling along the strong force chains preferentially, and therefore you're getting propagation through the center of the system, and that correlates with the global efficiency. However, in the scattering phase, you're finding that actually the signal is getting trapped in these local domains here. So the domain structure is really important during the scattering phase, when it's just sort of bouncing around in these local geographic states. So that suggests to us, this is something that we have not been able to see, this separation between injection and scattering phase, we've not been able to see with other statistics. So it's giving us some new information. So the summary of that study is that we can indicate or represent these granular materials as networks, and then we can use these traditional graph-based statistics to quantify structure in a couple different dimensions, from the whole system to two-dimensional domains, one-dimensional curves, and zero-dimensional particles. And what's interesting is that these multidimensional structures can differentially constrain or predict the bulk properties of the material. So then the next question was, is this really, it's a simple translation of network statistics into materials, but is that smart, and is there any better way of doing that? So I want to tell you about one of the problems of that approach, which is that there are a lot of non-physical assumptions. Optimization function is ki kj over 2m, where ki is the strength of node I, so the average force of node I. Kj is the average force of node k, and then m is the average force in the network. So this is also called the Newman-Girvin null model, and that's traditionally what we would use. So to give you an intuition for what that means, let's take an example of a ring lattice. So here, let's pretend I have, again, a two-dimensional box, but now I'm just going to have a line of particles instead of a volume of particles. And I'm going to connect them all together with just a single link. So they're all in contact with one another. Then the force network looks like this, right? So I only have strong forces between particles that are consecutive in that line. And then the null model gives me a probability of any two nodes connecting that fills the whole adjacency matrix, right? So I have non-zero probability that any node would connect to any other node. And what that does, if we apply that to this particular problem, is that it gives us these two-dimensional domain structures that I showed you. But we have assumed that any particle in that two-dimensional space can connect to any other particle, right? So I put the new physics alert because now you can actually have particles here connecting to particles there, which is completely unphysical, right? So it's not new physics, it's actually wrong physics. So then the question is, if we actually take into account physics, can we get a more accurate picture of what the structures are here? I wanted to say that this illustrates a bigger problem that I'm really interested in, which is that the field of network science is built traditionally on non-physical nodes and edges. And so I really think that there's a lot of space to radically revamp that toolbox to account for physical structures and physical laws, physical rules. So that's kind of my soapbox. I think there's a lot of work to do here, and I think it's really interesting. Okay, so how can we fix that problem? Let's do the first sort of non-stupid thing, which is that we're going to, again, look at this ring lattice structure. And now what we're going to do is we're going to take a null model that maintains the same contact structure. So nodes can now only contact to their immediate neighbors. But we wash out the structure of the forces. So the actual continuous variable here that quantifies the amount of force between particles, now we just take the mean right? So we're going to define our null model now to be omega, which is the mean force, times the adjacency matrix, or the contact network itself, okay? So that's really simple, right? So what do we actually get? If we use Newman-Girvin, we get this. If we use this null model, we get chain structures, okay? Beautiful. And it actually enables us to separate out different chain structures. So we can see boundaries between chain structures. We can now quantify what their shapes are, how strong they are. This particular plot, the color indicates how strong or how much average force there is in the particular chain structure. So we think this is really nice, and we think that it's a way of extracting the force chains themselves in a set of problems where that has been difficult before. And it obeys the underlying physical laws much better than this does. Okay, so then I wanted to tell you that in the optimization of the modularity quality function that enables us to extract these communities of particles, we can actually put a omega here, or sorry, a gamma here in front of the null model, which is called the structural resolution parameter. And if we do that, then we can actually tune the size of communities that we're looking at. So if we tune it up, we can get smaller communities. If we tune it down, we can get bigger communities. And that enables us to quantify spatial scales, different spatial scales inside of the packing. So here's just an illustration. At various values of that resolution parameter, gamma, we get different answers for which force chains exist. Yes, go ahead.
Sorry, when you tune the parameter, you're dropping a lot of nodes.
We're not dropping, all the white space? Yeah, the white space is single particles are their own communities. And so we deleted them as sort of a trivial part of the solution.
So your quantity Q there decides by itself what's the optimal number of communities?
Yes.
Zero, or it would be
Yeah,
where n is the number of particles?
that's right. Yeah. But that can be tuned somewhat using this gamma parameter, right? Yeah.
The color code is the force?
The average force in that chain. Yep. So then the question is there, it's very interesting to be able to extract structures at different resolutions, but we'd like to know if there's one resolution that's sort of most accurate in representing the structure there, right? So is there a way for us to choose this resolution parameter in a data-driven fashion so that we can just say what is the structure we should be looking at given the data? So to do that, I wanted to think about what kinds of structures we're interested in, right? We're interested in these force chains. What do they look like? What is their shape? Do they look like lines? Do they look like blobs? Or do they look like branches? Well, they look like branches, right? So what are some distinguishing features, shape features, between these three different kinds of objects? For a line, we thought about the fact that the hop distance, which is how many hops it takes to get from a node to another node, is actually equal to the physical distance. So to get from here to here, that's one hop, but it's also one physical unit. To get from here to here, it's 1, 2, 3, 4, 5 hops, and it's also 5 physical units, right? So the hop distance and the physical distance are identical in lines, right? In blobs, it's the same thing. So the hop distance between this side and this side is going to be 2, but that's also 2 physical units away as well, right? So this is the interesting part, which is where the hop distance is actually greater than the physical distance. So if I want to get from here to up here, I have to go through 1, 2, 3, 4 hops, but it's actually only 1 physical distance away, right? So these branch-like structures have this interesting feature, which is not present in these non-interesting shapes that we don't really care about very much. So what we'd like to do is to be able to use this fact to choose the resolution parameter in the modularity optimization. So here's just a little illustration of that. Here is the hop distance, so the topological path length, and here's the physical distance. And what we're interested in is when the hop distance is larger than the physical distance. That's where we get these branching structures. So in order to quantify that, what we did is we defined this gap factor. And the gap factor here is defined as 1 minus RC, which is the Pearson correlation between the two axes there. so the hop distance and the physical distance inside of a community. And we weight that by the size of the community divided by the largest community inside of the packing. So this SC over S max is a normalization factor. The sort of driving bit here is the correlation between hop distance and physical distance. So this enables us to, when that value is high, it points to objects that look like this, and when that value is low, it points to objects that are more compact or more linear. So we quantified that gap factor here as a function of the resolution parameter of modularity maximization. And what you can see is you get a really nice curve that has a distinct maximum. So what this suggests to us is that the resolution parameter that really captures the structure in here that is most branch-like occurs here at about 0.9, or 0.7, sorry, 0.7. So that gives us a way of identifying the resolution in a data-driven manner at which the most branch-like communities appear. So for future purposes, I think we can use that point and sort of disregard the low resolution and high resolution points for questions that are really focused on the force chain structure itself. So then what we did is we asked whether that gap factor can relate to, oh sorry, yes?
How specific is that going to be to
The packing?
to the system?
Yeah, that's a good question. A little bit is the answer. So it is fairly consistent over pressures of the same kind of system, and it is roughly similar between laboratory packings from Danielle's group and frictionless simulated packings from Lisa Manning's group. So they vary by a little bit, but not a lot.
I don't think friction's a big. Are you suggesting friction might not be a big issue here?
I don't think it's a big issue in defining where the resolution is that's ideal, but it actually hugely changes the shapes of these curves, and I'll show you that. Yeah. Any other questions at this point?
Are these perfectly round in the simulation, in this experiment?
Are what perfectly round?
The grains.
The grains. No, because they're being pushed on, right? So they're not perfectly round. Before they are perfectly round. Yes, they start perfectly round.
Not quite.
Well, okay, it depends how you want to define perfectly.
They're not like sand. They're not. Yeah.
No. So they're disks.
Yeah.
If that's so, they're two-dimensional. Yeah, they're disks. Why do you say not perfectly?
I think errantry tells me
What the error is in the actual. Yes. Okay. They are meant to be perfectly round. They're close. Yeah.
What are you resolving? I mean, the distance between particles?
We are resolving the size of the force chain. What is the size scale in the system? You can think of it as a size scale that is most representative of this branching structure. And the size scale can be identified as in the maximum of this shape curve. So then the question is, can it do anything for us, right, other than identifying a nice resolution point here? So here what we did is that we asked how that curve changes as a function of pressure. So what you can do is you can take that two-dimensional set of particles, and then you can put a brass bar at the top and push down on the particles with different amounts of force, right? So you can squish them more or less depending on the weight of the brass bar. And so that gives us packings of the same particles, but at different pressures. So here you can see at the structure at a low pressure and then at a high pressure as a function of resolution. And just by eye, you can see a few things. So as we go from low pressure, we get a lot of holes, and then at high pressure, we don't get as many holes. And then you can also see at the higher resolution parameter, at low pressures, we get more like lines or chains. And then at high pressure, we get usually dyads and sometimes triplets. So the gap factor is over here. So you can see in blue is low pressure. So that's the curve that I showed you on the previous slide. And you do see a distinct maximum here. And then as you go up to the higher resolutions, you can see that the shape of that curve changes. And we do see that the peak moves a little bit over to the right, but stays roughly at so it depends. There is a variation, but it's not as large as the variation across resolutions here. And what I want to point out is that independent of this maximum, which we can identify at any pressure, and therefore we can identify which resolution is important at any pressure, we can also see this function on the side where the gap factor decreases at higher pressures. So we can see that both there and on the right-hand side, so the left and right-hand side of the plot. And what that indicates is that the amount of branchiness is decreased at higher pressures than at low pressures. And that's exactly what we see here, right? So the amount of branchiness is quite high here, and then down here we get more to compact blobs, right? As you push and push and push, you're just going to get to a compact packing. And that's exactly shown in this gap factor as well.
Are these how are these loaded with the pressure? Are the beads just put in at a given pressure?
They're put in at just gravity, so with no pressure, no brass bar on them.
Oh,
and
I see. So these are vertical.
They're vertical, okay. Yep. And then the brass bar just pushes on top. So what's nice about the data is that it is the same packing but squished. So there is a sense that we could actually look at that structure continuously, and that's actually what Chad's going to mention. Yeah.
There's the resolution where it looks like it's almost invariant under pressure. Do you see that kind of often, where the curves will almost go through a single point? Yes. Does it really depend on what you're looking at? Is that just coincidence, I guess?
No, I mean, to me, I actually think that that's not as interesting, because I can tell. I would like to have a feature on the y-axis here that better distinguishes, even, that doesn't collapse at any particular pressure. And we think we have some ideas for that, and Chad's going to mention that as well. But, and that kind of depends, so for the frictionless packings, which I'm going to show you here, they actually collapse over many different resolutions. So these are frictionless packings from Lisa Manning's group, and here are the pictures of the force chains that we can extract using the community detection. And you can see just by eye a lot more similarity across different pressures than you see over here in the real packings, right? This you can see a drastic change as we go to high pressure. Here, the pressures are exactly the same, but we don't see by eye, at least, a huge difference in the packing structure. And that's replicated over here in the gap factor curves, where they lie on top of each other to a large degree. There is some variation on the tails, you can still see, and the variation on the tails is in the same direction as it was in the laboratory packings, which again suggests that you do get more homogeneity, more blob-like structure in the high pressure situations than in the low pressure situations, consistent with your intuition. But what's interesting about this is that we think that the tool can actually, or might be useful in distinguishing different types of packings. So the curves that we get from the two different packings are very different from one another. So then we wanted to follow up on that idea a little bit further. And here what we did is that we took the gap factor, but we also took two other measurements of each of the force chains. The size, which is the number of particles inside of the community, and the network force, so the average force on the particles inside of one of these communities or force chains. And here you can see the laboratory packings, making a nice data set here, and then the numerical packings from Lisa Manning's group here. And you can see that we can distinguish them very easily in this three-dimensional space. And I've separated each of those factors out here, so you can see actually each of the factors is pretty good at distinguishing. So the size of the chains is much lower in the laboratory packings. The average force is lower, and the gap factor is lower as well. So this suggests to us that we can actually use these to distinguish different types, this set of statistics, to differentiate different types of packings. Okay, so we think that the overall idea here is that we have some practical utility in three domains. One is that we have a framework for understanding which features of the force chains are universal versus which are governed by particular particle-particle or particle-environment interactions. It provides a tool to predict differences in macroscopic behavior based on subtle changes in the force chain diagnostics. And then it's also a methodology that provides new information on which particles are strongly connected within communities and the spatial distributions of force chains. And potentially we think that there are two questions we'd really like to ask, which are the boundaries between these force chains mechanically unstable, right? If we're able to identify the boundaries between them, that suggests that there's a weakness there, because the community detection is finding strong links and setting boundaries at weak links. So we're really curious about whether those boundaries are mechanically unstable. And secondly, are large, strong force chains mechanically stable? So can we look at the packing and identify sections of stability and sections of instability based on the spatial organization of the force chains? So that's where I have right now. I want to leave some time for Chad to tell you the new directions, but before we go there, are there any other questions on the stuff that I showed? Yeah?
It seems to me that the force chain model is referring the case when the strong force number of elements is sparse, right? Model, right? Rather than the original modularity model.
The null model. So we're using the geographic null model instead of Newman-Girvin.
Right.
Yeah.
Just wondering if that model would also make some sense when we have high pressure. Because all the
Here.
forces are more spread out.
Yeah, I mean, possibly, but interestingly, even with the geographic null model, we get the two-dimensional domains here. You can see them, right? So I'm not entirely sure whether it would bias anything else to use the Newman-Girvin. We could ask the question of whether we get the exact same answer or not. That would definitely be an interesting question. I really like the approach of the geographic model because it maintains the physical contact structure, but randomizes or sort of washes out the structure in the geometry of where the forces actually are, right? So you maintain contacts, but then mess up the geometry. And I think that's it's much more physically fulfilling, right, than the Newman-Girvin, especially if we can still get the two-dimensional domains at high pressures. But it's a good question. Yeah.
Do you have any idea how well these force chain networks correspond to the eigenmodes of the system?
No, that's one of the questions we have. Yeah, obviously we're speaking with Lisa, so yeah, we don't know exactly. What we'd really like to do, and what we think is possible, is to use these features to identify where soft spots are in the material. That's sort of the next problem that we're trying to work on. It's a hard problem, but we think that there is a relationship there. Yeah, Randy.
Do you think it's good that, so I look at this graph and I think, wow, high pressure is good because it's really strong in peak.
Yeah.
But I'm not sure that that's the right metric for saying it's good. What's good? Is it good that it's strongly peaked, doing things at high pressure? Is that better for detecting the structure?
But it's peaked at low pressure. You mean the gap factor peaks at low pressure too. So the good part is that what's good about this is that there is a peak identifiable at any pressure, and it tells us in a data-driven way what the spatial scale.
I mean that it's narrow.
Oh, that it's narrower in high pressure. Is that good or bad?
Yeah.
And you think it's good because it's better peaked?
Yeah. If there's noise, then you can see the structure better.
Yeah. I mean, I think what that's actually saying more about is that the structure inside of the high pressure situations is much more homogeneous across resolutions, so the shape doesn't change a lot across spatial scales. And I think that's why you get this peak here. Whereas for the low pressure situations, the shape does change significantly at different spatial scales. And that's what you're able to see with the broader, yeah.
Are you done?
Yeah.
Do you think the three-dimensional situation will be essentially similar? Do you
It
think
is,
it'll be
yeah.
totally new phenomena in 3D?
We can see some of the same things.
So you have some, it's like you have some results.
We have some three-dimensional simulations that, that not real data, but not laboratory data, but simulated data, and you do see similar structures. And the gap factor has a similar shape as well. We can still identify peaks that show the spatial scale of the force chains. There are some interesting differences too, but roughly the method works in 3D.
Have you tried any experiments with the frictional particles with shearing or anything like that?
We haven't yet.
Chain structure is different,
Right. We have not tried that yet. The other kind of data that I think would be really interesting is when you start reconfiguring it. So Karen Daniels has these particles on an error table as well, and so then you can pull out one and see it rearrange, or pull out a few, or push it in various directions. And in that case, we can have contact networks that vary over time and reconfigure, and I think those are really interesting questions. There may be different features that we can extract at that point, but we haven't looked at it yet. Yeah?
I noticed in the beginning you sort of chose a statistic for each dimension. So you've got the point level, the curve level, and then the I guess 3D domain level.
Yeah.
Is there a reason you just want one for each dimension? Like why stop at 3?
No, yeah, actually in that first paper we have 21 different statistics.
Okay.
Yeah.
Okay. So this is sort of
This is the highlights.
Okay.
Just to illustrate the fact that we can pick out different spatial scale or different dimensions using these statistics. Yeah.
So if you do something, so you have, if you consider all these 20, 21 different statistics and you
Yeah.
do PCA, do you see anything interesting?
If we what?
If you do all these statistics
Yeah.
in the network and you get distributions of numbers, for example,
Yeah.
or you can get an average, for example, for its statistics.
Mm-hmm.
If you do something like principal component analysis.
Oh, on the
do you see
statistics.
anything
Oh, that's interesting. No, we didn't try that. What we did do was to ask over a large set of packings, are there some of these statistics that are more that are less variable across packings, and are there some statistics that are more variable across packings? And that, we wanted to kind of identify really robust signatures of that type of packing. And the modularity actually is the one that was the most consistent across packings at an identical pressure. And so that's actually what made us sort of move forward in that direction. It doesn't mean that these other ones aren't interesting and that variation across packings is important, but we were sort of wanting to initially focus on what are measurements that are fairly consistent, fairly robust. Yeah.
Can you comment a little bit on the one, the local loop structure?
Yeah, so the clustering coefficient is can be thought about as the number of triangles divided by the number of connected triples in a binary network. In a weighted network, it's the strength of the triangles divided by the strength of the triples. So basically, you can think about it as when particles actually connect up into a triangle. So that gives you, it really only takes information at that very local level of connections within local neighborhoods, right? Only the neighbors of a particular node. And so that's why you get zero-dimensional information rather than these higher dimensional structures.
You identify where strong falls 3 peaks.
Yeah, exactly. Yeah. Yeah.
That's a good question. I mean, I'm going back to the outer application, which was, let's look at acoustic transmission through one of these materials.
Mm-hmm.
So I have a hard question. Maybe
Okay.
tell me to shut up. My question is, how do you know that when you see these force structures, it's not just that those guys are set up to report that the acoustic wave is passing through, but in fact the majority of the energy is going somewhere else?
Is
Right.
dissipating in the weak sections, you mean?
Right, that's right.
Mm.
And so those guys are sort of primed to report by birefringence that an acoustic wave has passed through their little path.
Mm-hmm.
Doesn't necessarily say that that's the dominant way in which energy gets from the underside of this material to the top side. That's where you should tell me to shut up.
That's a really good question. We haven't quantified the amount of energy that is dissipated through either force chains or the radial structure. I mean, from the picture, you can definitely see both, right? So I don't think, if you're asking, are the force chains the only story, I don't think that they are the only story.
So the picture biases what you right? And so it's a kind of compelling picture that you see this.
Yeah,
This
it's
path,
this
but it's
this one.
also
Yeah.
By virtue of the fact that those guys are close, they're the guys that are reporting the birefringence.
By the fact that they're close, I don't know. I mean, there are equally numbers of weak particles as the strong ones. So I don't think. And when you actually watch it, they do preferentially go along force chains, but they also go radially. So I think it's actually a combination. What we wanted to do was to have a data-driven way of extracting the force chains, and then we can actually quantify how much. That's the next step, is to ask how much of that information goes through force chains versus not. But to do that, we needed to find where the force chains are, and that led us to the method development.
So we showed that movie.
Yeah. You want to do it again?
Like some of the probes are not where it looks like there's force, right? Based on
Right,
based
oh,
on
that's true.
references.
Yeah.
So can you verify that in fact there's no force there? There's no distortion, right? So some of your probes
Yeah.
are in dead spots,
Yes.
right?
Yes.
So that would be another.
That would be a way to
Those are
clarify.
laser
Yeah.
recorders.
Yeah, they are.
But you should be able to do that with the numerical simulations, right?
Yeah, we could do that too. Yeah.
I mean, you know, put some friction
Sure.
into there are good models out there, and then you can just drive it and see.
Drive it. Yeah. Yeah, we could definitely do that. Yeah. All right. One more question, then I want to give Chad some time. Yeah.
Make this question silly. What sort of material do you use? What is the stuff?
What is this
Can you
stuff?
determine something?
Yeah, it's plastic. Plastic.
They're
Yeah.
made carefully to be round? Or
Yeah. They're laser cut by a laser printer. You can make any shape you want. There's stars and hearts and circles. Yeah, we haven't done any of the more complicated shapes yet. We've just done the discs. But that's another interesting question: is what kinds of packings you get at that when you change the physical structure.
Okay, so I'm just going to tell you a little bit about what we're currently doing in sort of a different direction. So I'm a topologist by training. So when I see problems like this, I immediately want to apply all of this heavy machinery. So I have a if you're looking at these force chains, so now let's imagine that we've done all of Danny's hard work, and we've got these force chains, right? So they're really networks. We can ask, what sort of statistics, what other statistics are there that might see something going on physically inside of them? So here's just a cartoon. You notice that right, what we want, what the gap factor is sort of picking up is that there are all these branch points at the interesting sort of resolutions. So what happens to those branch points? Well, you sort of have two different kinds of behaviors, right? You have these sort of loosely packed branches where the particles are off a bit from each other, and you look at that and you say, okay, so if I came along here and I poked one of these particles, it's going to be much more likely to slide than if I poke, say, this particle, because there's a strong force holding it in place. And what people have observed in previous work is that if you have one of these densely packed triangles in the graph, that actually increases the rotational stability at that point. So the chain, if you're coming along in the chain, so you got a straight chain and then you have a triangle in the middle of it, that'll actually be slightly more stable than if you just had the straight chain. Whereas down here, if I have one of these things, it's pretty clear that if I give that a poke, it's going to be more likely to shift. So, right. So these are two different sort of events that can happen in these force chains, the ones that we're looking for. But I look at that as a topologist, and I say, man, that looks a lot like stuff that I'm used to looking at. So these branches are loops in the force chain, and these guys up here, what are those? Are cliques, right? So what should I do? I should compute some sort of clique complex and do some homology, right? So that's exactly what we're going to do. So I just take the clique complex on that graph, which is only going to contain two cliques in below because it's this nice two-dimensional planar graph. And I'm going to look for these branches, but then you notice that I missed this branch down here, right? There are these other edge branches, so we can sort of introduce a correction factor to pick those up and make them into loops by just taking all the leaves in the graph, which indicate branching points that are sort of external, and quotienting by that vertex set, right? And now I'm going to get loops that correspond to these sorts of branches as well.
I mean, that's like the uniform external pressure infinity.
Something like that, yeah. I'm just sort of thinking of it as, right, I get to a certain point and the chain disintegrates because there's sort of loose material down here that it's evenly pressed against. So in a uniform sense. So, okay, so we can just define so I can just count the number of loops now. I'm just going to take Betty 1. but what I really want, right? I don't just want to count these loops. I want to tell you, right? If everything, if I have a whole bunch of triangles, that's a super stable object, right? So Betty 1's going to be 0. Whereas if I have a whole bunch of these kinds of loops, then it's going to be very unstable. So I want some sort of normalized measure, right? Also, force chains come in a ton of different sizes. So you want some sort of normalized measure. So there's an obvious thing to normalize by, right? There's the Betty number is the rank of a quotient vector space. So let me divide out by the size of the ambient vector space. And I'll get a number between 0 and 1, which tells me how close I am to being all of these or all of these. So, okay, so that's the proposed statistic. You might say, well, so I should say, and then we want, right, some sort of large statistic for the entire collection of force chains. So we do some sort of normalized sum, and it's just analogous to the thing that we do with the gap factor to get a system-wise statistic. Okay, so now you look at this number and you say, well, you're counting branches. Didn't the gap factor just count branches? But there's something else happening here. So we've really thrown away all of the physical distance information now. And in doing so, right, so this is just a scatter of many, many, many experiments across many different pressures and so on and so forth. We see that there's pleasantly no correlation at all between this new statistic and the old statistic. So we didn't accidentally just make up the same thing. It's seeing something new. So what is it seeing? So, right. So here's the first thing that we've. So this is, like I said, this is ongoing work. But here's what it seems to see. So these are the same experiments from before with the multiple pressures, right? The bar sitting on top of the thing. And if we go to this resolution factor right in here, right, the sort of physical good branch factor, resolution factor, we see that if we compute these statistics, so these little bars are standard deviations, it stratifies the pressure. So this thing plucks out the pressure that the system was under directly from the, right, just from the force chains. So somehow the ratio of triangles to loops is a good way to tell how much pressure the system is currently under.
What about that weird crossing point?
Yeah, I don't know what's happening over there. Some kind of thing is occurring way out there. I think, right, so what happens out here? Once you get to a certain point out here, the chains start to become, they start to disintegrate, right? And you get little tiny nubs instead of anything long and interesting. So
I'm saying pressure lines cross.
yeah, right. So at that point, I don't know. Oh, you right here.
Yeah, I mean,
Yeah.
you can say it's stratified too, also.
Sure. But I think this is just this is sort of consistent with what we think, right? That's where the force chains are look like force chains. So this is sort of where I would like things to stratify nicely. Yeah, they do stratify out there, and right here, I don't actually know what's happening out there. To be honest, I'm not a physicist in any sense of the term.
Does this work for different shapes, or would it only work for some things?
I could not tell you. I have literally no intuition on that. I would assume it would work for some shapes. If you were close to a circle, then I believe it would work. If you're some kind of crazy non-convex whatever, then.
What about polydispersity?
What about?
I mean, if you have different size particles
Oh, yeah.
all around with different size.
Danny?
These are bi-dispersed, so there's two different sizes of particles, but we haven't done more than two sizes.
Just to keep them from crystallizing.
Well, I think it's mostly for simplicity.
What's the ratio? Why couldn't you use monodisperse?
Oh, because of crystallization.
Right.
Yeah. I thought you were going to say crystallization at polydisperse.
No.
What's the ratio of the two sizes?
So they're 9 millimeters and 11 millimeters.
Okay, so all right, so this is just sort of the initial idea, but you might say, why did we go to all the trouble to bring homology into this? These are just graph computations. It seems like a lot of work. So the interesting questions are dynamic questions. And so if we alter the structure over time, if we increase the pressure or we add the shear force or something like that, then, right, if we do it just a little bit at a time and take measurements, we're going to get sort of sequences of snapshots of the state of the system. What we'd like to do is build some sort of statistic that makes sense in that setting. Well, everything important is up here. Right, so if I've got just this one network and I do all the community detection on it, then I get the, I get the force chains, etc. But you can do a more complicated version where now I've got some sort of parameter that I'm varying. And you just, you make your modularity function way more complicated looking, just essentially by adding these colored links here. So every particle is now linked with itself from time snap to time snap. And there's some, you have various parameters that tell you, well, this is how strongly you're linked from time to time. And then you have to vary all of these parameters and find the right one that gives you some sort of sensible answer. Right, but now what have you got? You've got a sequence of community structures or force chains structures in the material, and you know which ones are which. In other words, this force chain became this force chain, became this force chain, became this force chain. Right, so that's sort of a dynamic community structure or a dynamic force chain network. And if you are using something like homology, as opposed to sort of the more numerical network statistics, then you can play fun games by looking at refinements. So I've got two community structures. What are those? Those are partitions of the vertices. And I can look at the common refinement, right? I just intersect those. Really, I want to take the equalizer of those two community structures. And then I get induced maps on the homology, which lets me keep track of who is who, right? Which loops persist, which loops die. And as I vary the pressure, right, then I can glue them together over time. And there's this notion of zigzag homology in the applied topology community. So we should be able to sew together sort of persistent statistics on cycles as these communities evolve. So this is sort of the step that we are in the process of implementing. But it should give us a nice notion in the time direction of the change in force chain structure that should be consistent with this pressure information that we previously had at the very least. So anyway, so that's where we're going.